Look up on a clear night, far from the glow of any city, and you will see a few thousand points of light scattered across the dark. It feels like a lot. It feels like the universe is crowded, close, almost neighborly. But those few thousand stars are a rounding error, a whisper compared to the roar. Our galaxy alone holds somewhere between 200 and 400 billion stars. And beyond our galaxy, there are, by the most careful estimates we have, roughly 2 trillion other galaxies, each one a city of stars in its own right. If you tried to count every star in the observable universe, one per second, you would still be counting long after the sun itself had swelled into a red giant and swallowed the Earth. And so the question that every thinking person eventually asks themselves on some quiet night comes back with a kind of physical force. With all of that, with all those stars and all those worlds circling them, are we really alone? And if we're not, why haven't we heard from anyone? I want to spend the next half hour or so walking through that question the way a physicist walks through it, which is to say, not by guessing, but by taking the tools we've built to understand space, time, matter, and the origin of the universe itself, and asking what they tell us about the odds of ever hearing a voice that isn't our own. Because here's the thing I've come to believe after years of thinking about this. The answer isn't simply aliens don't exist, or aliens are hiding from us, or any of the more cinematic explanations you've probably heard. The answer, if there is one, is woven into the very fabric of space and time. It has to do with how big the universe is, how fast light travels, how briefly any of us, human or otherwise, might exist relative to the age of the cosmos. And possibly, if certain ideas in theoretical physics are right, whether elsewhere even means what we think it means. So let's start where I always like to start, with Einstein, and with the strange, counterintuitive nature of space and time themselves. Before Einstein, the picture of space and time that most physicists carried around, the one inherited from Newton, was comforting in its simplicity. Space was a fixed stage, an unchanging grid stretching out in 3 directions, the same for everyone everywhere. Time was a universal clock ticking away in the background, the same tick for you, for me, for a being on a planet orbiting a star 1,000 light years away. It was democratic, it was intuitive, and it was wrong. Einstein's great insight, first with special relativity in 1905 and then with general relativity a decade later, was that space and time are not a fixed backdrop against which the universe unfolds. They are dynamical. They stretch, they bend, they warp in response to matter and energy, and this is the part that still gives me a small jolt of vertigo, even after decades of working with the equations. They are woven together into a single 4-dimensional fabric we call space-time. Time is not separate from space. It is the 4th thread in that fabric, and how quickly it passes depends on how fast you're moving and how deep you are in a gravitational field. This isn't philosophical hand-waving. We've measured it. Put an atomic clock on a fast-moving jet and fly it around the world, and when it lands, it will have ticked off very slightly less time than an identical clock that stayed on the ground. Put a clock on a mountaintop and one in a valley, and the one on the mountain, farther from the Earth's gravitational pull, ticks faster. GPS satellites have to correct for this every single day, adjusting their onboard clocks for both. Their speed and their altitude, or the whole system, would drift into uselessness within hours. Time, in other words, is not a universal metronome. It's personal. It depends on your history through space-time, on your velocity, on the gravity you've experienced. And once you really absorb that, the whole question of contacting another civilization starts to look different, because it means now, for a civilization on the far side of the galaxy, isn't even a well-defined concept that lines up with our now. There is no cosmic wall clock we're all glancing at together. Now layer onto that the second piece of Einstein's legacy. Nothing, as far as we know, travels faster than light. Light moves at about 300,000 kilometers every second, which sounds close to instantaneous until you remember how big space actually is. Light from the sun takes about 8 minutes to reach us. Light from the next nearest star system, Proxima Centauri, takes over 4 years. Light from the center of our own galaxy takes about 26,000 years. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes 2.5 million years. And these are our close neighbors, cosmically speaking. If there is an intelligent technological civilization anywhere else in the Milky Way, and if they sent a radio signal toward Earth the moment they developed the capacity to do so, that signal is very possibly still traveling, still years or centuries or millennia away from ever reaching one of our telescopes. And if we send a message back, our reply wouldn't arrive in their lifetime, or possibly not even in the lifetime of their species. This is the first deep obstacle, and it's not a technological one that some future invention will simply dissolve. It's baked into the geometry of space-time itself. The speed of light isn't a speed limit we haven't yet found a clever way around. As far as our best tested physics is concerned, it's a fundamental feature of how cause and effect propagate through the universe. So even setting aside whether anyone is out there, the architecture of space and time makes conversation in any ordinary sense of the word almost unimaginably difficult. A dialogue requires a message and a response within a time frame that means something to the participants. But if your nearest potential conversational partner is even a few hundred light years away, you're not having a conversation. You're leaving a message in a bottle and tossing it into an ocean so vast that the bottle might wash up on a shore centuries after you yourself have turned to dust. Any contact we might have with another civilization would almost certainly be one-directional, a signal received from a civilization that may have already changed beyond recognition or ceased to exist entirely by the time we detect what they sent. Now let's push the timeline back even further, to the very beginning, because the Big Bang has its own lessons to offer here. About 13.8 billion years ago, as best we can tell from the cosmic microwave background radiation, from the abundance of light elements like hydrogen and helium, and from the large-scale structure of galaxies we observe today, the universe began in an extraordinarily hot, dense state and has been expanding and cooling ever since. In the earliest fractions of a second, the universe may have undergone a period of extremely rapid inflation, stretching space itself at a rate that dwarfs anything we can intuitively picture. As it expanded and cooled, quarks combined into protons and neutrons combined into the first atomic nuclei, and eventually, after about 380,000 years, the universe cooled enough for electrons to bind to nuclei and form neutral atoms. Light, which had been trapped in a hot, dense plasma, was suddenly free to travel. And that ancient light is what we now detect as the cosmic microwave background, the oldest photograph we have of the infant universe. Here's why this matters for the question of aliens. The universe needed time to make the ingredients for life. The Big Bang produced hydrogen and helium and just a trace of lithium. Nothing more complex. Every other element, the carbon in your cells, the oxygen you're breathing, the iron in your blood, the calcium in your bones, had to be forged later inside the nuclear furnaces of stars and then scattered across space in the violent deaths of those stars, in supernova explosions that seeded the interstellar medium with heavy elements. Only after generations of stars had lived and died could there be enough carbon and oxygen and nitrogen and phosphorus floating around to build planets, let alone biology. Our own solar system, at 4.6 billion years old, is itself a product of earlier stellar generations. This means that for a significant stretch of cosmic history, the early billions of years, the universe may simply have lacked the raw material for life as we understand it, no matter where you looked. The window for complex chemistry, and then for life, and then, vastly less probable still, for intelligence capable of building a radio telescope, only opens gradually, and it opens at different times in different parts of the galaxy, depending on local conditions. That timing problem compounds with everything we just discussed about the speed of light and the finite age of the universe. Consider two civilizations, both perfectly real, both intelligent, both curious, both scanning the sky. If one of them arose 8 billion years ago and burned brightly for, say, 10,000 years before going extinct, a blink cosmically speaking, and the other us, arose only in the last 100,000 years, then there was simply no overlap. No amount of searching would have found each other, because by the time our radio telescopes were built, that other civilizations' signals had already passed through this region of space and moved on, or their civilization had already ended long before Earth even finished forming. This is sometimes called the temporal Fermi paradox, and I find it honestly one of the most sobering ideas in all of astrobiology. It suggests that even in a universe teeming with life across its history, the odds of two intelligent technological civilizations existing at the same cosmic moment within communicating distance of each other could be vanishingly small. Space is vast, but time is vast too, and we tend to forget that the fourth dimension is just as unforgiving as the other three. This brings me to a very famous question, one posed almost as an offhand remark by the physicist Enrico Fermi over lunch with colleagues back in 1950. If the universe is so old and so large and the ingredients for life are, as far as we can tell, common, the same physics, the same chemistry, the same elements everywhere we look, then where is everybody? Given enough time, even a civilization expanding modestly, colonizing nearby star systems over tens of thousands of years, could in principle spread across an entire galaxy within a few million years, which is a cosmic eye blink relative to the age of the Milky Way. So if intelligent life is even moderately common, shouldn't we see some evidence of it by now? Megastructures, radio leakage, some unambiguous technological signature, and yet the sky, as far as our searches have shown so far, is silent. There have been countless proposed resolutions to Fermi's paradox, and I don't think we should pretend any of them is settled. Some suggest that life itself is common, but that the jump from simple microbial life to complex, intelligent technological life is the truly rare step, what's sometimes called the great filter, and that we may have already passed through the hardest part of that filter, or that it still lies ahead of us, which is a genuinely unsettling thought if you sit with it. Others suggest that intelligent civilizations tend to be short-lived, that the very technologies which allow a species to broadcast its presence to the stars, nuclear energy, artificial intelligence, biotechnology, are the same technologies that carry existential risk, and that civilizations tend to burn out or destroy themselves shortly after becoming detectable. Still, others point out quite reasonably that our search has barely begun. We have scanned only a tiny sliver of the sky at only a narrow range of frequencies for a relatively short span of decades using instruments of limited sensitivity. Absence of evidence in this case is really not strong evidence of absence. It may simply be evidence that we haven't looked nearly long enough or in the right way. But I want to bring in one more idea, one that comes from my own corner of physics, from string theory, and from the broader landscape of theoretical cosmology, because I think it deepens the mystery in a way that's worth sitting with. String theory, for those unfamiliar, is an attempt to unify all the forces of nature, including gravity, into a single coherent framework, by proposing that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and that these strings vibrate in a space-time with more dimensions than the three of space and one of time that we experience directly. In most versions of the theory, there are 6 or 7 additional spatial dimensions, curled up so tightly, so small, that we simply don't perceive them in ordinary life, much the way a garden hose looks like a one-dimensional line from a great distance but reveals a second circular dimension when you get close enough to see its width. One of the strange, and to some physicists, uncomfortable implications of string theory is the existence of what's called the landscape, an enormous number of possible ways those extra dimensions could be curled up, each one giving rise to a universe or a region of a much larger multiverse with different values for the fundamental constants of nature. Combine that with the physics of eternal inflation, the idea that the rapid expansion in the early universe may not have happened just once, but may still be happening in some larger cosmic structure spawning countless separate expanding regions or bubble universes, each potentially with its own laws of physics, and you arrive at a picture where our entire observable universe, everything we can ever, even in principle, see or measure or communicate with, might be just one bubble among an inconceivably large, perhaps infinite number of others. If that's true, and I want to stress this is still very much a hypothesis, not an established fact, then the truest sense of cosmic isolation isn't just about distances measured in light years within our universe. It's that there could be an unfathomable number of other universes potentially teeming, with their own stars, their own chemistry, their own intelligent beings that we are not. Merely far from, but permanently, physically disconnected from, separated not by distance, but by the very structure of reality in a way no future technology could ever bridge. It's a strange kind of loneliness isolation, not measured in light years, but written into the geometry of existence itself. Even if we set aside the multiverse and stay within our own single observable universe, there's a related and more immediate consequence of space-time structure that's worth understanding, because it means our isolation may be built in even here. The universe is expanding, and that expansion is accelerating, driven by whatever we're calling dark energy, for lack of a better understanding of what it actually is. As space itself stretches, galaxies that aren't gravitationally bound to us are, in a sense, being carried away and beyond a certain distance called the cosmic horizon. Galaxies are receding from us faster than light can cross the intervening space to reach us. This means that there is a boundary, a genuine edge to the observable universe, beyond which we will never receive a signal, no matter how long we wait, no matter how sensitive our instruments become, because the space between us and them is growing faster than light itself can close the gap. And troublingly, that boundary is shrinking. Billions of years from now, an astronomer on Earth, or whatever remains of Earth, will look up and see far fewer galaxies than we do today, because most of them will have crossed beyond the cosmic horizon, redshifted into invisibility, causally disconnected forever. We happen to live at a relatively fortunate moment in cosmic history where a great many galaxies are still visible to us. That won't always be true. In some very real sense, the universe itself is slowly closing doors on the possibility of contact, and it has been doing so since the beginning. So let's bring all of this together: the relativity of time, the finite speed of light, the billions of years needed to forge the elements of life, the staggering improbability of temporal overlap between civilizations, the sheer size of even a single galaxy, let alone the observable universe, the possibility of causally disconnected regions or even entirely separate universes in a wider multiverse, and the accelerating expansion that's steadily placing more and more of the cosmos permanently out of reach. When you hold all of that in your mind at once, the silence in the sky starts to feel less like a mystery demanding a dramatic explanation. They're too advanced to bother with us, or they're deliberately hiding, or some galactic quarantine is keeping them away, and more like a natural, almost inevitable consequence of the scale and structure of space-time itself. It may simply be extraordinarily difficult, not for lack of other minds out there, but because of the architecture of the universe those minds and we ourselves are embedded in, for any two pockets of intelligence to ever line up in space and time closely enough, and for long enough to say hello and actually hear a reply. And yet, and I want to end here because I don't think this is a depressing conclusion, I think it's a clarifying one. None of this means we are alone in the sense of being cosmically unimportant, or that the search is pointless. If anything, understanding just how special the alignment would have to be, the right amount of time since the Big Bang, the right elements cooked up in the right generation of stars, the right conditions on a rocky world at the right distance from its star, the right billions of years for complexity to accumulate into something that can ask the question, is anyone else out there in the first place, only deepens the sense of how remarkable it is that it happened here at all, even once. We are, as far as anyone can currently prove, a momentary local pocket of the universe that has become complex enough to look back at itself and wonder. Whether or not another such pocket ever hears from us, or we from them, that fact alone, that the universe produced beings capable of measuring the age of light and calculating the curvature of space-time and asking whether they are truly alone, strikes me as one of the most extraordinary things the cosmos has managed to do in nearly 14 billion years of trying. We may never get an answer from beyond, but the question itself and everything it's taught us about space and time and our own fleeting luminous moment within it might be the most profound signal of all, one we sent quietly to ourselves.